Hello, thank you for stopping by. My name is Karen Lee, and I'm an undergrad student at the University of Pennsylvania studying computer and environmental science. I worked with Marcel Hessing and Dr. Eric Eaton to study transfer learning in a multi-class classification setting in our paper, Land Use Prediction Using Electro-Optical EO to SAR Few-Shot Transfer Learning. We extend an approach that aligns embedding spaces of two neural networks using sliced Wasserstein distance by considering the properties of the neural network's internal representations. Our three main contributions are providing evidence that sliced Wasserstein distance embedding alignment can be scaled to multi-class problems, and that applying instance normalization and contrastive learning leads to better performance. The UN has estimated that a large proportion of SDG indicators can be measured through the use of geospatial data. For example, land use and land cover mapping can measure the health of populations, urban areas, and ecosystems over time. Synthetic aperture radar, or SAR satellite data, is extremely effective as sensors collect information continuously and are unaffected by weather conditions in the day and night cycle. Deep learning methods have shown tremendous success when transferring knowledge from one domain to another. In this work, we consider transferring representations trained on EO data to the SAR domain to alleviate the problem of data scarcity. We train on the SO2-SAT dataset, which consists of local climate zone labels for Sentinel-1 and Sentinel-2 EO and SAR satellite images. Originally designed for urban heat island research, the dataset consists of 17 total classes, with 7 natural classes and 10 urban classes, including 4 that are low rise. Our method builds on a previously suggested Y-shaped neural network to transfer knowledge from the EO to SAR domain. Outputs of identical EO and SAR encoders map to a shared embedding space. To align distributions in this shared embedding space, the method employs a sliced Wasserstein distance loss that leverages both labeled and unlabeled SAR data.
Okay, so let's take a closer look at our contributions. In this paper, we analyze additional settings as well as several extensions to the sliced Wasserstein embedding alignment. First, we consider more realistic and harder settings than previously suggested. For this, we have several difficulties of varying numbers of classes from the SO2-SAT dataset. During development, we found that the method is very sensitive to data normalization. As a result, we conjectured that not only normalization of the inputs is important, but also normalization of embedding spaces. Therefore, we test instance normalization instead of the standard batch normalization to handle the wide range of spectrum that comes with the SAR data within specific data points. Lastly, the idea of embedding alignment crucially builds on the fact that the learned EO embedding is sufficiently discriminative. However, there's no guarantee in more complicated settings that that is in fact the case. To alleviate this issue, we employ a contrastive loss that ensures that similar classes are mapped together while dissimilar ones are mapped further away from each other. So let's have a look at the result. First, we find that the original method outperforms all our baselines on the multi-class setting as long as we use instance normalization. To dig a little deeper into this phenomenon, we performed a second experiment. We showed that using instance normalization might in fact be required to achieve good results when doing embedding alignment with complicated SAR data sets. Finally, we show that the contrastive loss leads to improved SAR classification performance in almost all data regimes, even when applied only to the EO encoder. We argue that these three results compensate for some of the weaknesses of the previous approach by improving training stability and classification accuracy. They show that embedding alignment is in fact an interesting direction to explore for transfer learning research. This summarizes our work on few-shot learning for land use prediction. If you have any questions, feel free to reach out to us.